Hi, this is Involved Innovation YouTube channel. In this video, we will see about the basics of Kafka. Kafka is a distributed event streaming platform developed by LinkedIn, written in Java and Scala. It is open sourced in 2011 and now managed by Apache Software Foundation. It is designed to handle high throughput, fault tolerant and real-time data streaming. Kafka is widely used for building data pipelines, real-time analytics and other event-driven applications. The biggest selling point of Kafka is it can handle massive pipelines of real-time data, so it is better suited for mission-critical applications which deals with huge volume of data. The prime task of Kafka is to stream data. Here the data is the Kafka message or record. Each record is a self-contained unit of data that contains optional key, value and optional metadata. It is important to note that Kafka itself does not impose any specific data format for keys or values. It treats them as raw byte arrays. It's up to the producers and consumers to serialize and deserialize in the appropriate format. For example, data can be deserialized and serialized to JSON, Avro, protobuf, string, integer, etc. based on the requirement. The design allows Kafka to provide efficient message distribution, ordering, and fault tolerance while accommodating a wide range of data formats and use cases. This is how a Kafka message will look like. Key, it is a byte array and can be null. We will see more about the key and key serialization later when we discuss about producers. Next is the value, which has the payload you want to send. This can also be null, but logically this can't be null because you need to pass the payload. That's why you need Kafka. Then we can perform the compression in message. The default is no compression. Messages are stored and transmitted without any compression. It is useful when messages are already in compressed format or when compression is not required. Other compression types can be gzip, snappy, lz4, zstandard to compress the message. We can add optional headers which are key value pairs, partition and offset values. This is to define the partition number where the message goes to and then the offset number of each message. We will learn more about partition and offset shortly. Then the timestamp. This can be set by the system or by the user. Now we will see about different parts that constitutes Kafka. Broker. Broker is a core component of the Kafka system. Broker can be a physical machine or a cloud instance or a container. Group of brokers join to form a cluster. Group of brokers provide high scalability and availability. We will see how we can achieve high scalability and availability, fault tolerance with the replication later in the series. Each broker has an ID. One of the broker will be identified as Bootstrap broker, which will provide information about other brokers to the producer or the consumer. Topics are the fundamental units of data organization in Kafka. A topic is a logical channel or feed to which records or messages are published by producers and from which the records are consumed by consumers. If you are familiar with the message queues like ActiveMQ or RabbitMQ, here the topics can be comparable to queues or topics in the message broker. But remain in mind that it is more than that. With Kafka Topic, the messages can be broadcasted to a number of consumers. Here, the orders, shipment and returns are the topics. Producer can publish message to this topic and consumer can listen to these topics. Kafka topics are immutable. That is, once the data is written to a partition, it cannot be changed. Messages in Kafka are kept only for a limited time. This is configurable retention time. Default is 1 week and this is flexible. We can set any retention time. Even forever retention is also possible by setting the retention time to -1. Partitions. Each topic can be divided into multiple defined number of partitions, which are the basic units of parallelism and scalability in Kafka. For example, here the orders topic has 4 partitions and shipment has 3 partitions, returns has 4 partitions. Partitions allow Kafka to distribute and store data across multiple brokers, enabling efficient data processing and fault tolerance. Message order will be guaranteed in a single partition. If the messages are sent to different partition, then the message order won't be guaranteed. Each broker contains certain topic partitions. For example, broker 1 contains order topic partition 0 and partition 1. Shipment topic contains partition 0. Broker 2 contains order topic partition 2 and shipment topic partition 1. And broker 3 contains orders topic partition 3 and shipment topic partition 2. Message reaches a partition based on the message key. This key will be hashed with a hash function, and based on the value it will be sent to a particular partition. If there is no key provided, the message will be sent to partition in a round robin fashion. Offsets. The message order in an individual partition is guaranteed with the help of offset. Offsets are unique identifiers associated with each record in a partition. Offsets are incremented by 1 starting from 0. The offset number is unique to an individual partition. Each partition offset starts from 0 and incremented by 1 for each incoming message to that particular partition. Kafka retains records or message for a configurable amount of time. Consumer can choose where to start reading based on the offset. Offsets are not reused even if the messages are deleted from the topic. Producers. Producers are responsible for sending records to Kafka topics. Producer knows which partition it needs to read. We will see more about this shortly. Consumers. Consumers are responsible for reading records from the Kafka topic. Consumer use pull model, that is, consumer will actively request data from the Kafka broker. Consumer automatically know which broker to read from. Consumer use offsets to keep track of their progress in reading records from partitions. Data will be read in an order for a particular partition from low to high offset. Consumer need to know what is the format of key and value to serialize, because the key and value will be stored in binary format that need to be deserialized by the consumer. Next we will see about one of the very important topic, that is consumer groups. Consumers can be organized into consumer groups to work together on consuming data from topics. Each consumer group can have multiple consumers, and each partition in a topic can be consumed by only one consumer within the group. This enables parallel processing of data. For example, here the consumer 1 can read from partition 0, consumer 2 can read from the partition 1 and 2, and the consumer 3 can read from the partition 3. But important thing to note here is two consumers from the same consumer group cannot read from a single partition. If there are greater number of consumers than the partition, then the excess consumer will be in inactive state. There can be more than one consumer group listening on the same topic. For example, the consumer group 1 has 3 consumers and listening on the topic orders, and there is another consumer group 2 listening on the same topic orders. Each consumer group is identified by the group ID. Customer __ consumer _ offsets topic. This topic is a special internal topic in Kafka that is used to store and manage committed offsets of consumer groups. Consumer offsets are used to track the progress of consumer groups in a cluster, indicating up to which point a consumer group has successfully consumed message from each partition of a topic. This topic is managed by Kafka itself, and it is not meant to be directly interacted by the users. Kafka maintains the consumer offsets to allow consumer group to resume consumption from where they left off in case of failures, restarts, or rebalancing. The offsets stored in the consumer offsets topic help Kafka manage this coordination across consumer group members. The consumer offsets topic is considered an internal topic, and it is typically not exposed to users through standard topic metadata queries. Users interact with consumer offsets indirectly through Kafka Consumers API. By default, the consumer offsets topic is created with a single partition. Each record stores information about the consumer group, the topic, partition, and the committed offset value. The key contains group ID, topic name, partition of the topic, and the value holds the offset. Group ID is a unique identifier to a consumer group. Example group 1, name of the topic, example orders, and partition is the partition within the topic for which the offset is being stored. Example 1, and the offset is the committed offset value for each specified partition. For example 2. When a consumer successfully processes a batch of messages from partition, it can use the commit sync or commit async method to commit the processed offsets to Kafka. This involves sending a commit request to Kafka, which in turn stores the committed offsets in the consumer offsets topic. When a consumer restarts or joins a consumer group, it needs to determine the correct offset from which to start consuming messages. It uses seek method along with the seek to end or seek to beginning methods to fetch the offsets from the consumer offsets topic based on the group ID, topic and the partition. Next is the delivery semantics for consumers. The delivery semantics for the consumer refer to how messages are processed and acknowledged by consumers within the consumer group. Kafka provides several delivery semantics options that allow you to control how consumer receive and processes message while ensuring reliability, fault tolerance. There are 3 major delivery semantics for consumers. First one is at most once. In this delivery semantics, messages are consumed and processed by consumers and acknowledgements are sent to Kafka brokers before any further processing occurs. This means that there is a possibility of message loss if a consumer crashes after processing but before sending the acknowledgement. This mode is useful only when message loss is acceptable and minimizing duplicates is a priority. At least once semantics, consumers ensure that messages are processed and acknowledged before proceeding with further processing. If a consumer crashes after processing but before sending the acknowledgement, Kafka will re-deliver the message to another consumer. This guarantees the messages are never lost, but it may lead to duplicate processing if the application is not idempotent. This is preferred delivery semantics, and the message processing in the application must be idempotent. That is, if the same message is processed more than once, it should not change the state of the system after the first processing. The next semantics is exactly once. Kafka introduced transactional capabilities that provide exactly once delivery semantics. This is the most stringent delivery guarantee, ensuring that messages are processed and acknowledged only once. Even in the presence of consumers or broker failures, it requires the Kafka transactional API and coordination between the producers and the consumers. Next we will see about producing and consuming message from Kafka. This is the key thing to understand because producing and consuming message from Kafka is the real reason why we use Kafka. Now we will see how the messages are sent to the topic in a Kafka system. Let's take the producer sends the message to the order topic. Here the key is the integer, so we need integer serializer to serialize this value to the byte array. And the value is JSON, so we need JSON serializer to serialize the JSON message to byte array. The key will be hashed with the hash function. Based on the hash value, the message will be sent to a particular partition. One important thing to note here is if the messages with a particular key will always go to the same partition. This is important to maintain the message processing order guarantee in a particular partition. For example, here the key is 4234. Based on the hash function, the message will be sent to the partition 0. If there is another message with the same key 4234, the messages will be sent to same partition 0. If there is another message with different key, based on the hash value, this message will be sent to the correct partition. Now the consumer will pull the message. The message will be in a byte array format, so we need to deserialize the key with integer deserializer. Since the key is in integer format, the value is in JSON format, so we need to deserialize it with JSON deserializer. Next, we will see about topic replication. Topic replication is very vital to have durability. Topics must have a replication factor greater than 1 to reduce data loss and increase durability, fault tolerance, and availability. With this replication, if a broker becomes unavailable or crashes, then another broker can provide that information. Replication involves maintaining copies also known as replicas of topic partitions across multiple brokers within a Kafka cluster. This ensures that if a broker or partition fails, data is not lost and can be retrieved from one of the replica brokers. Here's how topic replication works. Each partition of a topic can have multiple replicas. Replicas are distributed across different brokers within the Kafka cluster. One of the replicas is designated as a leader and the remaining replicas are designated as followers. For example, here each topic has a replication factor of 2. Orders topic partition 0 is also replicated on broker 2. The partition 0 of orders topic in broker 1 is leader and the partition 0 of orders topic in broker 2 is follower. By this way, each partition will have a replica and these are distributed in different brokers. Kafka distributes replicas across brokers to achieve fault tolerance. Replicas of different partitions are usually stored on different brokers to ensure that a single broker failure does not affect all partitions. There is no point in having the follower replica and leader replica for a particular topic partition in same broker. The leader replica is responsible for handling read and write operations for a partition. All producers and consumers request goes through the leader. From Kafka version 2.4, it is possible to read from the in-sync replica. This is to reduce the read latency. Followers replicate data from the leader to stay in sync. If the reader fails, one of the follower can be elected as a new leader. Kafka uses a combination of asynchronous and synchronous replication to ensure that the data is replicated across replicas. Producers send data to the leader, which then replicated it to the followers. The replication is performed in the order of data arrival, maintaining message ordering. This guarantees the message ordering in a single partition even if there is a broker failure. In sync replicas, short form ISR, are followers that are fully caught up with the leader's data. So at any point in time, the leader data will be in sync with this ISR replicas. They are considered in sync with the leader. These replicas are eligible to be elected as a new leader in case the current leader fails. Followers that fall behind the leader are considered out of sync. They need to catch up before they can be eligible to become leaders. Kafka ensures that in-sync replicas are maintained to ensure data durability and availability and fault tolerance. If a broker fails, the leader and the follower replicas on that particular broker are unavailable. However, Kafka automatically promotes one of the in-sync replicas to be the new leader, ensuring that data remains available even in the face of failure. In this example, if the broker 1 becomes unavailable or crashes, then all the replicas and leader replicas in broker 1s for all the topics become unavailable. Here the partition 0 for the orders topic in the broker 1 is the leader, which become unavailable because of the crash. Now the partition 0 for the orders topic in the broker 2, which is an in-sync replica, which will be elected as the leader for the orders topic partition 0. The replication factor for a topic determines the number of replica copies for each partition. A higher replication factor increases data durability and availability but requires more broker resources and storage. Replication adds some overhead in terms of network and storage resources. However, Kafka is designed for high throughput and the asynchronous nature of replication helps minimize the impact on producer and consumer performance. Next we will see about producer acknowledgement. Producer acknowledgement refers to the confirmation that Kafka Broker provides to the producer after it successfully receives and stores a message that the producer sent. The acknowledgement mechanism ensures data reliability and helps producer know whether the message has been successfully persisted in the Kafka cluster. Kafka offers different levels of acknowledgement to cater various reliability requirements. There are three main levels of producer acknowledgement in Kafka. Acknowledgement, which is AX equal to 0, fire and forget. In this mode, the producer sends the message to the broker but does not wait for any acknowledgement. The producer assumes that the message has been sent and moves on to sending the next message. This approach produces the least reliability, as the producer has no confirmation that the message has been successfully received or stored in the broker. 1. Leader acknowledgement. In this mode, the producer sends the message to the broker and waits for the acknowledgement from the reader replica of the partition. This leader replica acknowledges the message once it is successfully stored in its local lock. The producer gets a confirmation that the message has been received and stored by at least one broker, providing better reliability compared to AX equal to 0 acknowledgement mode. AX equal to all or AX equal to -1. Full replication acknowledgement. In this mode, the producer sends the message to the broker and waits for the acknowledgement from all in-sync replicas of the partition. The producer only gets confirmation once the message has been successfully stored in all replicas. This level of acknowledgement provides highest level of reliability but may introduce higher latency due to the need to wait for multiple replicas to acknowledge. Next, we will see about the discovery. The discovery of partitions within the topic between the brokers are done using the Bootstrap broker. Bootstrap broker is an initial broker that a Kafka system such as a producer or consumer connects to in order to discover the rest of brokers in the Kafka cluster. Any broker in the cluster can be Bootstrap broker. It acts as an entry point for a client to find the metadata necessary to interact with the Kafka cluster. We will see how the Bootstrap broker works. Let's take your producer need to send message to the order topic partition 0. Producer does not know all the broker information. So the producer does not know in which broker the partition 0 is present. That is, the producer or the consumer does not need to know all the broker addresses upfront. It just needs to know the address of one broker to get started. That broker is the Bootstrap broker. The address can be specified either as hostname or IP address along with the port number. The default port number is usually 9092 for plain text communication. When the client connects to the Bootstrap broker, it sends a metadata request to the broker. The metadata request asks for information about the Kafka cluster, including the addresses of other brokers, topics, partition, and other relevant details. The Bootstrap broker responds with the metadata containing information about the Kafka cluster topology, such as address of all brokers and the available topics and the partitions associated with each topic. Based on the metadata received from the Bootstrap broker, the client now knows the address of all the brokers in the clusters. It can then establish connections to the appropriate brokers for publishing or consuming messages based on the topic and partition information. Kafka clusters can be dynamic, with brokers being added or removed over time. The metadata received from the Bootstrap broker may include information about brokers that have joined the cluster after the client's initial connection. Kafka clients periodically refresh their metadata to stay updated about cluster changes. Thanks for watching this video. I hope you have learned a lot about Kafka, the theory part. Stay tuned to this series to understand and learn more about Kafka, how to create producer and consumer with Java Spring Boot application. If you like this video, subscribe to this channel and share it with your friends. Thanks for watching.